Okay, guys, can you hear me again? Great. Let's continue with the second half, which are these characteristic functions. Okay, so characteristic function. We're on slide number 13. So characteristic functions. So what do we have? We have a random variable, and it has a distribution, which is the probability that x is less than some number over in the codomain. Its characteristic function. So its characteristic function is given by, and what we do is you take a number, t, which is in R, we map this thing into the expectation of I, t, x. Right, so just a thing that often becomes confusing is that t is not time. It's just a dummy variable. And so this number here is going to be, this is going to be complex. And one should also contrast it with the moment-generating function. So this is a similar map. You take a t, is inside R, you map it into, and then instead of it, you write etx. And this number here is a number between 0, but it could be infinity. Remember this one here, this is included, and that's the main problem. This is why we are preferring the characteristic function where you have this I here in front. It is to rule out, get rid of this potential problem of being plus infinity. Right, what we know is that if you look at an example, like the normal, if I take x to be standard normal, well then the expectation, does anybody remember what this is? Does anybody remember what that is? So it would be, yeah, Alice is saying e to the, so sigma is equal to 1, Alice, so it's going to be e to the t squared divided by 2. And does anybody remember what this one here is? maybe I can just cheat a little bit, share my screen, and try to do it in Mathematica. So let's, I'm hoping everybody can see my Mathematica screen now. If I'm looking at a density, which is equal to exponential of minus x squared divided by 2, divided by square root 2 times pi. And then I'm interested in the characteristic function, so that will be exponential. I'm interested in moment in a function, which is t times x times f of x. I'm going to be interested in this for x between minus infinity and infinity, and I want to integrate. So this is what Alice says should be t squared divided by 2, and that looks good, Alice, you're right. We could also be interested in the same thing when I squared it. So instead of the moment generating function for x, I will look at the moment generating function for x squared. And now we see there's a condition here that says that there's a limit to how big t can be. So it's going to be this quantity here. Let me just copy paste it on my piece of paper. I'll have root 2 divided by root 2 minus 4t, and this is for t less than a half. Okay, so let me stop sharing, and then this is for t less than a half, so we can simplify some of the stuff here. I think this should become 1 divided by root 1 minus 2t. So you see, t here is given to be real. T is given to be real, but it's only going to be finite when t is less than a half. So this thing here, when t gets to be equal to a half and bigger than a half, then this this moment generating function becomes plus infinity. This is the main reason for why we won't be interested in using the moment generating function, because it can be plus infinity. And this is the problem, right? So this is problematic. We won't have that problem if you're looking at the characteristic function. If I look at the characteristic function, so we should just recall that if I look at a complex number, let me call it z. This is equal to its real part and its imaginary part, right? So here we have, this is the real part, and this is the imaginary part. It's like a polar representation. Thinking about the real part, this is going to be A. The imaginary part, this is going to be B. Right, so both the real and the imaginary part are going to be real numbers, right? So the real part of C, this is my A, and that's a real number. The imaginary part of Z is going to be B, and that is also a real number. Like I here, this is the square root of minus 1. But there are other ways to express this. I could indeed do this polar coordinate trick, right? So I could write this here as, this is a number in the plane. There's a vector in the plane, so I can think about this as an ankle. You could think about this as an ankle and a length. If I think about it this way, I would have the length times, and then I would have the ankle, that would be my cosine of theta, plus, and then I sine of theta. Or if you want, you can write this, let me write that in red because we'll use it a lot. You could write this here as the absolute value times E I theta. Right, this here is Euler's form. But we have two ways of thinking about a complex number, right? We can think about it in terms of its real and imaginary components, or we can think about it as an angle and a length. And when I went to school, this was called the idiot rule. This was called the idiot rule. It says that if I take the absolute value of EI theta, this is going to be, well, it's the length of a number. Okay, so let me write out what the number is. The number is the absolute value of cosine theta plus I sine theta. Right, so this is equal to cosine squared plus sine squared square root. And what do we get here? Yeah, I was right. We're going to get a 1. So the idiot rule is when I take the absolute value of this Euler form, I'm going to get 1. So this is convenient because this is convenient. So this will give us, for us, this is important because if I look at the characteristic function of E, I, T, X, this is my complex number, right? So I can take absolute value, and if I pull the absolute value inside, I'll get something that is bigger. And then I'll use the idiot rule, and I'll get that this is 1. And this is true for any random variable. So it doesn't matter which one it is. You always have that the characteristic function takes values in the complex plane, but inside the unit ball. It always has length less than or equal to 1. So if we return to the two examples we have here, we have the normal and we have the normal squared. We had the moment generating functions. Now let's try to look at the characteristic functions. So the characteristic functions. So again, you take your x, it's going to be standard normal. And now I want to look at EITX. Any guesses on what that is? And any guesses on what this one is when I put a square? Well, one thing we can do is we can go back to Mathematica and see what Mathematica says. If I go up here and I'll put in an I, So if I take, I think I, capital I is the one you need for Mathematica. So if I put in a capital I here for the imaginary part, you see the change was, instead of having a minus sign, instead of having a plus sign, I get a minus sign up here. So the moment generating function is the one that have exponential of t squared over 2. If I put an I here, I'm going to get, let me just write it down, it's going to be e to the minus t squared over 2. And of course, I can do the same thing over here. I can put an I here and see what I get. All right, this is taking longer. Maybe this is not working on my computer. Come on. There you go. And this is the number we get here. This is equal to root, that's the same structure as before, 1 over root 1 minus 2it. And here the condition is that the imaginary component of t is bigger than minus 1/2, but for us t is a real number, so this is always true. Okay, so if I switch back here to my screen, this is what we had. And you see, this is always, this works for all t. And you can indeed see that the number here in absolute value, of both of them, is going to be bounded by 1. Right? You take absolute value here, I'm going to get something that is less than 1. One should also just, so here's a tempting but wrong, nevertheless wrong argument. Right, we know that, as Alice said in the chat, that if I do e of tx here, then this is going to be equal to e to the t squared over 2. So now replace t by it to get that e itx, that would then be e to the it squared divided by 2, which would be equal to I squared, this is minus 1, and you recover the formula we had up here. And you can do the same thing for the one down here. So this is tempting. In particular, it's tempting because it gives you the right answer. So sometimes one is eager to justify the means by the ends of, but unfortunately here this won't work. This is a wrong argument, and it's wrong because you only allowed to put in t's that are in R in the characteristic function. Sorry, you're only allowed to put t's that are in R for the moment generating function. You're not allowed to put it here inside this formula. So the correct route is a bit longer. The correct route is a bit longer, but let me try to show you one way of doing it using Ito's lemma. So you cannot, this is not allowed. This is not allowed because IT does not belong to R. It's the right formula, but it's the wrong argument. So I want to start by redoing the argument using Ito's lemma. So here's an argument for how to calculate the moment generating function using Ito calculus. So for us, we will use stochastic analysis or stochastic calculus to calculate characteristic functions. And we're going to start out by rederiving the formula that Alice mentioned, this one here. Okay, so how are we going to do it? Well, we're going to take a Brownian motion. So we're going to have B. We're going to have BU. Say U lives between 0 and 1. This is a Brownian motion. Okay, so you might see, this is just a note, 3 writes B view like this. I don't write all these parentheses, I put the U downstairs. So this is a Brownian motion, and then one of the properties of a Brownian motion is that it's normally distributed. So we'll then use that B1. This is going to be normally distributed with mean 0 and variance 1. So I'm interested in computing T at B1. Because this is standard normal, so I'm interested in calculating the moment generating function for a standard normal. So here are a couple of ways to do it. So here are 2 ways. Here are 2 ways. So the first one is you look at an object as ZU, and you probably already seen that when you took a class that had Brownian motion in it. If you've taken 485, you will have seen it there. If you've taken, for those of you that have taken already 622, you've seen it there. And for those of you that are currently taking 622, I'm hoping that you've seen it either this week or last week. But if you take an object and you exponentiate the Brownian motion, so you get a T here, and then you have BU minus, say, 1/2 T squared, and then a U. Okay. If you define this object here, and U is living between 0 and 1, well, then you get a martingale. So I'm going to see this 2 ways. The first one is, because we have a this particular setting, we can do it directly. So we can see this directly. If I look at the conditional expectation of, say, CU given Fs, right? So here U is bigger than S, bigger than 0, less than 1. Then what can I do? I will take the expression, plug it in here. I'll get e to the t bu minus 1/2 t squared u condition on Fs. Now, are there any guesses on how I should proceed from here? Well, how is it with Brownian motion? So have a u that is bigger than s. So u here is later compared to s. So I need to have a relationship between s and u BU is not going to be independent of Fs, but I know Brownian motion has independent increments. So what I could do is I could take the t, and then I could write BU here, and then I could subtract away Bs, because then I want to get the increment, and then plus a Bs, and then minus a half t t squared u given Fs. And then I can use that I have independence now. I can take out what's measurable. So the TBS goes outside. And here I'll have minus a half t squared u. And then I'll just have the unconditional expectation. And now what is this expectation? So we can use, I guess I'm circulating now. I'll use Alice's comment, see that this will be e to the 1/2 t squared, and then the variance is just going to be u minus s. And all in all, you will cancel out, I'll get ETBS minus 1/2 t squared s. But this here uses the moment generating function. So that's a drawback, right? I needed to go from here to here, and that used the thing that I'm actually trying to compute. So this method here is correct, but it does use the moment generating function, and this is what I'm trying to compute. So that's not too good. The indirect argument, so the indirect argument beats this one. And what the indirect argument is, it uses each lemma. And it does not use this moment generating function. It uses each's lemma to compute the dynamics of this argument here. It uses each's lemma to compute dzu. Okay, so how does that work? Well, we need to write, so you need to write cu as a function of bu. We put bu as a second argument. So it's writing this as a function of u and bu. So that's, if you want to use each's lemma, you have to find a function first. So what's the function? It's a function of u and x. What should we use for the function? Right, z is equal to et. So I'm going to get et, and I want to have, can I fit it on one piece almost? So I want to write zu as a function of u and bu. Okay, so the x here goes up there, and I have minus 1/2 t squared, and then I have my u. So that's my function that will take me from time and Brownian motion. I combine them using this formula, and it's going to spit out what z is. So to use Ito's lemma, I need to compute derivatives. I need to compute f1 applied to u and x, right? So remember, at least for me, this is the notation. You take the derivative with respect to the first entry. So this is the u derivative of f of u and x. And what is that equal to? So I need to look at the function, take a derivative with respect to u. It's an exponential, so you're going to get the exponential back. That's u and x times, and then the derivative with respect to u minus 1/2 t squared. I need the derivative with respect to the second entry. So this is the derivative with respect to x of f, u, and x. Okay, the function, I need to take the derivative with respect to x. The function is an exponential. I'm going to get the exponential back, f, u, x, and then times the derivative of what's inside. This will just be a t. And then the new thing with e to lemma compared to standard calculus is that you also need the second derivative with respect to the x variable. So this is the second derivative. This is the second derivative with respect to the second entry, f22, fux. I need to take the derivative of this quantity here with respect to x. I'll get fux t squared. These are the ingredients that we need to use e to lemma. So e to lemma will allow us to compute the dynamics of z using these expressions here. All right, so e to lemma now. So e to lemma it gives us that this dz is going to be equal to, and then I need all the derivatives. The first one is f1 of u, bu, and then du, plus there's f2 u, bu, dbu. And then we need the higher order term because Brownian motion has only finite quadratic variation. So you need a half here. And then it's f2 to u, bu, and then the quadratic variation of Brownian motion, which is du. So that's e to lemma in this particular form. And now we plug in all the derivatives that we carefully computed. And we'll see in all these derivatives, f is the common value. So here we will have f of u, bu, and then curly brackets. The first one is to do with time. That's going to be minus 1/2 t squared, and then a du. The second one, this is just a t times that f we have outside the curly brackets, and then it's dbu. And the third one is 1/2, and then the double derivative, that's going to be t squared, and then du. And now we can see what happens is that two of the terms, they cancel. There's a minus 1/2 t squared here, and there's a plus 1/2 t squared here. So these two terms, they cancel, and you'll be left with, well, first of all, this was my z. This was a zu t dvu. And of course, when you write it in this d form, there's nothing else, and you can integrate both sides and say that zu is equal to z0, and then an integral of dzu. And this will give you z0. And then you have zu, there's a t, go outside. This t should not be up there. This u here should be up there, and then this here should be, say, s. And you see that z is a constant and a stochastic integral. And stochastic integrals, you know that these guys here, are martingales. So this shows that z is a constant plus a martingale. So constants are, of course, martingales. You'll get that c is a martingale. And here we did not use the moment generating function to say anything about this. We got that this object over here, we got that was a martingale. Are there any questions on the Ito calculus calculation we did here? I know for some of you, this is very, very new. For some of you, you have seen it maybe a while ago. We'll do one more calculation that is quite similar to the one we just did. And then at some point, you're going to be doing them in the homework. So I'm hoping that at least at this point we are convinced there was a direct argument and indirect argument. This object here, this is really a martingale. Because, so now we're done proving that. So because all martingales, they have a constant expectation. We get that Z0 is equal to the expectation of Z1. Right, but that's the same. If I look at what Z was, I plug in U equal to 0. Then Brownian motion times 0 is 0. U here is 0. This is e to 0. That's a 1. So this is the same thing as saying that 1 is equal to the expectation. And then Z1, okay, so over here on the right-hand side, U is equal to 1. I get ETB1. And then I get minus a half t squared. And this will allow me to move. This is deterministic. It has nothing to do with, this is not random. You pull it out on the other side, you'll get e to the 1/2 t squared is equal to e TB1. And that's what we wanted. So this here is using martingales to calculate the moment generating function. In other words, if you can use Ito's lemma, we can get this moment generating function. Are there questions about this? So now we're going to try to do, this here gave us the moment generating function. Now we're going to try to do the same type of calculation, but we want to get the characteristic function. So we're now going to adjust. We're going to adjust the argument. We're going to adjust the argument to get to compute the characteristic function. Right, so this is the expectation of E, and then now we have an I here, TB1. So now we have the I, and the argument has to be different. And so what was it we had before? We had a nice martingale. This was our martingale from before. How should we adjust it? Well, now, so now we have a martingale, so we should look at CU. Any guesses on how we should adjust this martingale to to the case that we're interested in now, when we have an I here. Before we had a TBU, now we probably need an I here. Okay, so we're going to write this here as an E and then an I, TBU. And then what we have over here is a minus a half, and then it's IT squared. IT squared, so it's going to give me a plus T squared times U. Right, so we're claiming, well, we'll factor out the common factor. This is e to the 1/2 t squared u, and then this, so this here is Euler. Euler's form. This is Euler's form, so here we will get, it'll be cosine, and then it'll be t bu plus I sine t bu. So we're claiming that this here is a martingale. Right, it's going to be complex value, so we need to check. So we need to see we need to check that both these components, so we're going to get e to the 1/2 t squared u cosine t bu. That was the first part. And we need to check that e to the 1/2 t squared u, and now we have sine t bu. We need to check that both these guys here are martingales. Okay, so this time we're just going to use Ito's lemma, like we did in the last step before, and prove that it's a stochastic integral with respect to Brownian motion, and that will give us the claim. So let's consider cosine, the cosine part, right? So let's write. So first you need to find a function. First you need to write e to the 1/2 t squared u cosine t bu. We need to write this here as a function of time and Brownian motion, where the function, where's the function? We need an exponential. This is going to be e to the 1/2 t squared u, and then you get your cosine tx. Right, so it's similar, but not quite the same as what we had before. The function we had before was this etx minus 1/2 t squared times u. So it's similar, but this e to the tx, this has now been replaced by a cosine to tx. Other than that, it's the same. So to use Ito, we need the derivatives. We need f1, u and x. F1 of u and x, we need to compute the derivative here with respect to u. This will be e to the 1/2 t squared u cosine tx, and then the derivative is going to be 1/2 t squared. And then you need f2, the first derivative with respect to x. So what are we going to get now? We're going to get the exponential terms out there. And then we need to remember what is the derivative. What is the derivative of cosine? Derivative of cosine, is that sine or is it minus sine? I always forget. Does anybody remember the derivative of cosine? Is that sine or minus sine?
Minus sine.
Minus sine, we put a minus out there. Tx, and we have to remember to take the derivative with respect to what's inside. Tx's derivative with respect to x is t. And then you need f2 too. So you need to take the derivative of this thing here with respect to x. So now sine's derivative is going to be cosine. There's a minus sign sitting out there. So this is minus e to the 1/2 t squared u. Now we're going to get cosine here. And then we need to take the derivative again, so we're going to get a square here. Alrighty, so what are the dynamics of the left-hand side here? df of u comma v. Let's write it all out. This is f1 u bu du plus f2 u bu dbu. And then we need the extra term because the first variation of Brownian motion is plus infinity. The second variation is finite. You get f22 here. And then the critical variation of Brownian motion is time. You're going to get du there. And now we plug all these derivatives in there. And you can see this exponential factor is common, so I'll put him outside curly bracket. So f1 here, this is 1/2 t squared du. And then I need f2. This is minus t dbu. And this here is minus t squared times 1/2 du. So as before, the miracle happens, and these two terms, they cancel out. And we're left here with e to the 1/2 t squared u. There's a minus sign, and then there's a t, and there's a dbu. Because of this calculation, we now have that. What do we have? We have that. I have my e to the 1/2 t squared u cosine tbu. This was my f. This was equal to f at 0, b0 plus, and then an integral from 0 to u of df u, and I should call it s maybe. And so I'll plug in what that is. That b0 is 0, so get a 0 there. Get an integral, and there's a minus sign, minus t e to the 1/2 t squared s dbs. f0 at 0. Let's just write out what that is. This is cosine at 0, that's a 1, so I'm getting a 1 here. Half t squared s dvs. And this here is a martingale. So we are in now the same situation as before. I know now that the expectation, so the expectation of this quantity here, e to the 1/2 t squared cosine t b1. This is a martingale, does not have any expectation. This here is equal to 1. So all this stuff up there implies that I was able to compute what the expectation of this quantity here was. Any questions or comments on these martingale calculations that we've been doing? Alice is asking where the sign went. I don't know. Did we miss it? Sign. Oh, it should have been right here. Huh? It should have been right there. That should have been sine t bu. Yeah, I lost that one in the calculation. It should have been sine t bu d bu. Just a hint. Whenever you have a d on the left hand side, make sure that all the terms on the right hand side also have d's. Right? There's a d here. Got to be a d here. Got to be a d here. Got to be a d here. Whatever you do, if there's a d on the left hand side, there got to be a d on the right hand side. This term here was missing. Thank you, Alice. And it's probably going to be missing on the next page too. It should have been right here. It should have been sitting right here. Let me put it in. This is sine t bs dbs. The same thing here. Thank you. Are there other questions? So we had two martingales. We had two martingales, right? So we did this one. So you can try this one here yourself. So similar. We're gonna get the this as a martingale, and that will give us that the expectation is so that I take u to be 1 sine t b1. That's going to be the initial value. This is e to the 1/2. So that's t squared, the initial value. So this is times a 0 times sine TB0. So this here is a 1, a sine, this one here, this is equal to 0. This is going to give me a 0. So overall, I'll get that this martingale, so now this is a martingale, it's a complex valued martingale. It has a real component and an imaginary component. Both components are martingales. I'll now get that the expectation of Z1, I'll get here that the expectation of C1, I'll have a Z0 is equal to the expectation of Z1. Z0, that was the one we already had. This is a 1. This is equal to, this here is equal to the expectation of E, and then what was it? It was this ITB1 plus this thing, ITB1 plus 1/2 T squared. And again, this part here is non-random. We'll now get that this is e to the minus 1/2 T squared. This is the characteristic function of ITB1. And way back, this was the same expression that we had in the, we got from Mathematica. This was way back on slide 15, right? That was all the way back there. We'll have that we had a normal, we would get the characteristic function to be this e to the minus t squared over 2. And that's exactly what we see here. Are there any questions or comments about what we did here? We all good? Okay, then what we're going to move towards is an inversion formula. So this is, we're not going to have time to do that today. That'll be next time. But so we're going to have this characteristic function. So, what we need. So we need a formula called the we need a formula which returns so the distribution. So it returns the distribution function from the characteristic function. So this is called the inversion theorem. So let's just try to apply it. Let's try to apply it in this example. So if I tell you that EITX is equal to e to the minus t squared over 2, if I tell you this for any t in R, you can tell me that the probability of x being less than x is equal to what? That's right. Meow was right. This is equal to n of x. This is equal to 1 over root 2 pi integral from minus infinity to x. So this is one of the cool things. This is why it's called the characteristic function, right? This explains the name. Characteristic. It's a characteristic function. So we need a formula, right? This is just an example. Right? You need a formula that will take us from this characteristic function back to the distribution, or maybe even the density. But you can see there's like, you look at this thing, and now down here there's like a 1 over root 2 pi. I mean, how do I get from there to here? And that's this inversion theorem. There are, of course, many other applications of characteristic functions. There are many applications. There are many other applications of characteristic functions. If you're in analysis, you have a background in engineering, often we have students that have some background training or a lot of background training in engineering, and here they have been taught Fourier transforms. So we call them in probability, they call characteristic functions; in analysis and in engineering, they call Fourier transforms. There are many applications of them. We're going to be looking at it in this stochastic wall setting, but you can also use, like, there are more, another practical application is something like often you will check, you need to show you need to show that x is independent of y. So you can also use characteristic functions to do that. And the way to do it is to look at E, and then you would have your I, say T1 times X, plus IT2 of say Y. If the joint, this is the joint characteristic function. Right, so here we're looking at 2 time points, T1 and T2. So this is a point in R2 being mapped into this thing, which is something that lives in the complex numbers. It has length less than or equal to 1. This is a joint characteristic function. So if you want to check that x and y are independent, this happens exactly if and only if. So often you need to show this, then x is independent of y if and only if EIT1 of x plus IT2 of y becomes the product. If and only if this is true for any T1 and T2 in R. So there are many applications of characteristic functions. In analysis, it's this Fourier transform. In probability, this is a basic application of a characteristic function. It allows you to test for independence if you can get something like this to work for any T1 and any T2. So here's a brain teaser. A brain teaser would be does it suffice to consider T equal to T2 to show that X is independent? In other words, is it okay just to be on a diagonal? Here it says for any T1, comma T2 in R. The question is, does it suffice, for example, to just look at T1 being the same thing as T2 to show independence? Right, so that could be a brain teaser. Anybody figure this out? So what I wanted to say with these couple of slides here is what we need for stochastic volatility models is we need to be able to go from the characteristic function back to the distribution. So we need this inversion theorem. So this is next time. The last few minutes I want to spend on an obstacle that we're going to encounter next time. So when you work with this inversion theorem, there is an obstacle that comes up quite often. So for this inversion formula, there's a tricky interval, and the interval that we're going to be looking at is this one here. There's this integral that appears, and I think for those of you, some of you have seen this in If you're taking my classes, there will have been a homework about this integral here. This is like the simplest example that I know of where it's not the simplest. It is a simple example of a case where there is a difference between improper Riemann integrals and integrable functions. So I should say versus. Very often one uses these two things interchangeably. Here, unfortunately, there's a difference. So let's start with the improper Riemann integral. The improper Riemann integral. Here you're looking at, in that case, what you would have is this integral this is a limit. This is a limit of integrals of this form. Here we should just make a note. There are two possibilities for bad behavior, right? It's going to be around 0 and around infinity, right? So just a note here. If I look at the integrand around 0, so if I look at the limit as x goes to 0 of sine x over x, I can use L'Hopital's rule. And it says you compute derivatives. So this is going to be the limit as x goes to 0. And then we want to have cosine of x up there. And you want to have a 1 here. So this is going to be 1. So there's no, the behavior around 0 is not the problem. It's the behavior out here near infinity. And it's of course true. It's also true that if I compute the limit at x as x goes to plus infinity of sine x over x, right? Sine x is going to be bounded in absolute value by 1. I take something that is bounded, divided by x, take x to infinity. This here is going to be 0. But not all decaying functions are going to be integrable. And this here is an example of one of the bad ones. So if you do the improper Riemann integral, this here is going to be a limit of a quantity like that one. If you do the integrable functions, if you want to look at the integrable functions, then we'll need to have the integral from 0 to infinity of the absolute value of sine x divided by x, that this is less than infinity. And this is problematic. So let me try to give an illustration of why this is problematic. This here is false. This here is false. If I look at the absolute value of sine x over x, like x is positive, what I will do is sine x, sine at 0 is 0, so I'm going to get something here. This here is my sine x over x in absolute value. So I get the first bubble, and then it goes down, but I take absolute value, so I'm going to get another bubble, and a third bubble, and so on. And what happens when I add up the area of all these bubbles? Well, this is problematic because inside here, I could put a box, and I could put a box in here, I could put a box in here, and so on. Now, how big can I make these boxes? How big can I make these boxes? I should be able to make this box here of size what? So if I would write this, integral, then I would have to see sine is periodic, so there's 2 pi here. So maybe this is 4 pi. Is that right? Sine, no, this should just be pi. So right, sine of pi should be, sine of 0 is 0. Sine of pi over half is 1. Yes, I think this is right. So I'll break this integral. Right, I'll break this integral here up into a bunch of terms. I'll sum over k. I'll sum over k, and then I'll have an integral from k equals 0 to infinity. So I'll have a k times pi to k plus 1 times pi. And sine x in absolute value divided by x dx. How would I do that? Well, I'll bound x here. I want to make this thing here smaller, so I could put in a bigger x. This here would be bigger than if I would sum from k equals 0 to infinity of k plus 1 divided by k, and then I'll have sine x here. Instead of x, I'll put in a bigger number. I'll put in k plus 1 times pi. Now, when I integrate sine x, I'm going to get the same thing over all these intervals because I'm not dividing anymore. And the problem, of course, being that if I sum up from k equal to 0 to infinity of 1 over k plus 1, what do I get? Of course, this is the same as summing from 1 to infinity of 1 over k. What does that become? Does anybody know what the sum of 1 over k, summing from 1 to infinity, what does that equal? Maybe we can switch over to Mathematica, see what Mathematica says. So here, if I would do sum of, say, 1 divided by k, k 1 to infinity, it says it doesn't converge. It's going to give me the value plus infinity. So this value here is plus infinity. So this function here is not integrable. So it's not true that this is finite. This is indeed equal to plus infinity. And so we have, it's not going to be an integrable function. What about the improper integral? What is this integral here? It is defined as this limit. Is there a limit here of these things? So it's defined as a limit. This is the limit as n goes to infinity of these integrals. Okay, so then we could try to compute what that is. And maybe we could, we're running out of time, but let me just show you what Mathematica would say to something like this. If I were to integrate, sine x divided by x from 0 to infinity, what would I get? And you see, Mathematica spits out pi over 2. So let me write that here in on my slide. So this is Mathematica. It says that this here is pi over 2. This is Mathematica, at least for now. Mathematica says that this is pi over 2. So we have a situation where the improper integral is well defined, but the integral is not defined. Okay, so the function is not integrable, but the improper Riemann integral is well defined. So it's this friction here that appears whenever you study these formulas that are coming out of the inversion theorem. There's always this problem that the integral that appears in these formulas, it is not the integral of an integrable function, it's one of these improper Riemann integrals. So it's just something to keep in the back of your head. If you've seen examples like this before, then that would be great. If you haven't seen them, try to play with this before next time, because next time it's going to be an issue that we have to address. We are out of time. Are there any questions here before we call it a day? Otherwise, we will have office hours tomorrow morning. Are there any questions before we call it quits? Okay. I wish everybody a happy weekend. If I don't see you tomorrow morning, otherwise I'll see you guys on next Thursday. Have a good day, guys.